I teach an advanced Go optimization workshop, and I've run it dozens of times, and I know exactly what's wrong with this code and exactly how to fix it. But what I wanted to know is, can AI also figure it out? Not by guessing, but actually profiling, measuring, and proving every change. So let's find out. Hey, I'm Corey Lanoux, and I build AI-powered developer workflows. So here's the code that I've got in the background. It's a word counter from my optimization course, and it reads Hamlet. It counts the total words and distinct words, and it's deliberately terrible. It has single-byte reads, string concatenation in a loop, no buffering. It is a performance horror show, but that's on purpose. The entire point of this workshop is to show all of my students how to use the tools to identify, not guess, what is wrong with their program. Now, I know the exact steps to fix this, and I've walked students through this over and over. And first, you're going to profile with pprof. You're going to find the single byte read. You're going to fix it with a bufio reader. Then you're going to profile it again. You find the string concatenation. You fix it with the bytes.buffer. And then you keep going. It's one change at a time. You measure every change with benchstat at every step to compare the previous runtime metrics to the current runtime metrics and understand, did you get better or worse? That's the discipline of profiling. You never guess, you always measure. And the question is, can Claude Code follow the same discipline if I just give it the right tools and the right rules? Or even better, can it do something I would not think of? So here's the prompt that I'm going to give it. And basically, I want it to optimize this Go code for performance. I've given it the tools available that I want it to use. And then I've given it the rules. I told it that it has to test after every single pass and make sure it still works. I want it to only make one change at a time, then profile it, fix it, benchmark, compare, and repeat that. I wanted to save every benchmark and run a profile to the benchmarks folder. Number them sequentially so compare them later and after every single run. And then I only want it to search the internet based on what the pprof showed it. So I don't want it to go out and start to find all kinds of profiling and best practices. I want it to be event driven based on only what it's finding. And then when it's done, it's going to provide a play-by-play list of every command it ran in the order it ran it, so I can trace through how it uncovered each of these issues. Again, I want to see, will it uncover something that I haven't uncovered in the past? I've taught this course many times. I also want to understand if I can learn anything from this process, right? That's always a great way to use AI. All right, so I opened up Claude and I gave it the exact prompt that we just went through. Now, I already ran this, so we don't have to wait for it to go through, but we can kind of walk through piece by piece and see what it started to do. Now, the first thing it did, it spotted several potential issues, but it's going to follow the rules first. That's the important piece of this. And it's going to start by running a baseline test and establishing the benchmark for the CPU profiling. So it goes ahead and runs that, and it comes back and it identifies the thing that we always identify in this exercise, and that is that we are using all of our CPU time in the words.read rune. And the read rune function is doing a 1-byte syscall read for every single character. And so that's a huge bottleneck. And what's interesting about it is it very quickly identifies that it should wrap the reader in a bufio.NewReader. Now, this is a common pitfall that I spot in a lot of code when I'm reviewing it, especially for people that are new to the Go ecosystem. They don't realize that readers aren't buffered automatically. And that's on purpose in the Go ecosystem. They don't want to assume that you want to buffer things. So just by adding the bufio.NewReader, it makes a huge difference. So they run this and they see they had a 94% reduction in time and a 42% reduction in allocations. All right, that's great. So now it's going to profile the new code, which is what I told it to, and then it's going to go ahead and look at it. Now, what it's finding is after it profiles it again, that syscalls are still the dominant flat cost, but the per op time dropped by 94%. So when that happens, we know that we're really not bound by the CPU anymore. And so it actually figured out to drop to the benchmarks for allocated objects, which is doing a memory profile. That's the exact same thing that happens when I teach this course. So far, it's following along just like a human being would follow along, which is pretty cool. Now, the next thing it finds is that 100% of the allocations are in the words.count. That's the string concatenation, which is really, really inefficient Go. And why is that? Because anytime you manipulate strings, you're creating brand new memory, because strings in Go are immutable. And that's something I think a lot of new people that Go miss. And the profiler picked it up and the AI picked it up immediately. And so what it's going to do is it's going to switch to a strings.Builder. All right. So that's going to be the way to do that, a strings.Builder. And that's actually something I don't do. So I actually switched to ruins instead in my code, and they switched to a strings.Builder. And it's interesting to see that that actually worked faster than just converting to runes from strings. So I was interested to see that it did actually catch something that I haven't caught before, and that's a good one. So if we come down, we see how that worked. Again, that was a huge reduction, 48.6% reduction in time, but the big one was 87.9% allocation reduction. Now, here's the cool part about that. It really was a memory fix, and that memory fix, because we're no longer allocating memory, ends up being also a clock fix, right? It ends up being a huge performance fix for the CPU because we don't have to allocate memory. So remember in Go, anytime you can reduce allocations, you're going to make your code faster because you're not manipulating memory. All right, so if we come down here, now we're going to see that we're now dominated by syscalls again. It looks like the strings.Builder.WriteRune is growing its buffer. So to address this issue, it wants to read the entire input at once to eliminate the IO syscalls, and it's going to use a pre-allocated byte slice instead of a strings.Builder. Now, I have a little bit of an issue with that. I don't like pre-allocated byte slices because in this case, we're guessing about how big that byte slice is going to be. And so when it comes to performance, we don't like to guess. Is it going to make the code faster? Yes. But this is just the shape of the data now for this one specific run with the Hamlet text that we're reading in. What happens when we read different text, smaller text areas, bigger text areas? Now, again, that initial byte slice that we're making here isn't really big. I think they're doing a 1096 on that byte slice if I look at it. And so that's not huge. But again, I just really don't like anytime we pre-allocate those types of slices. So again, that's what they're going to do here. They're going to run it, and it does actually increase the performance, right? But not as much. So our allocations are down a little bit more here at 17.3%. So now at this point, the CPU profile is really dominating with the garbage collection. And so that means that really allocations are our issue at that point. And it knows that by looking at this string data of how it's actually using this map lookup. So what it wants to do is it already avoided allocating strings for the words we've already seen. Now it's going to jump in, and it has decided that unsafe.String is going to be the better way and get rid of map lookups for no allocations. I can tell you right now, as soon as I see unsafe, that is a code spell and go, especially for something like this. So we were doing pretty good, I think, up until this point, and now the wheels just came off the bus, right? Like everything just went crazy. Not what we want to do. So unsafe is definitely not something that I would recommend, especially for something like this. And then it actually caught that it had to upgrade the Go mod. So this is a really old exercise I do. And it actually had to update this to 1.22. Even though 1.26 is the current, that's fine. I would have liked to see it go to a 1.24. I usually try to be 2 versions behind the current release. But again, AI really struggles with that as well. So what did it do? It dropped allocation by 62%. I would expect that, but really it did it the wrong way. I'm really unhappy with what it actually did at this point. And let's see, now one more thing it did, which I thought was pretty cool that I never thought of doing, is we have to be Unicode compliant, right? So I want to make sure that we read UTF-8 properly. And I'm using the UTF-8.decode rune all the time, but that's kind of a heavy operation. So what it's going to do now is actually detect, is it UTF-8 or not? If it's not UTF-8, meaning it's just ASCII, it can create these 2 little functions which are really, really quick. And these will make it so it's much faster to detect, is it a space or not? This was a really nice optimization. Now, if we were in a big performance bottleneck, this would be a great optimization, so one that I didn't see before. So again, while it went off the rails with the unsafe, this was actually kind of a cool fix. The only thing I don't like about this is now look at how much more complicated the code's starting to get. Yes, we're optimizing it, and yes, we're making it faster, but now we're sacrificing readability. And that's another big issue. So when we optimize code, readability is still really important. Because if your code is hard to read, it's going to be much more likely someone introduces a bug to it. We don't want that. So again, I would look at this and say, I don't know if I like this too much because this code's getting really, really hard to read at this point. But did it do optimization? It certainly did, and it certainly helped out the code quite a bit better. All right, so where did we end up at the very end of the day here? So it looks like at this point, it's just finishing up its optimizations, and this is where it pre-allocated that map, by the way, and which I did not like. All right, so it did that. Okay, so it looks like it figured out that it was starting to hit diminishing returns. And that's really important because when you optimize, you can go forever. You can never stop. And Go was actually smart enough to figure out that it hit diminishing returns. And where did it actually end up when it's done? It did some pretty cool stuff. Before, it was taking about 69 milliseconds per operation. It finished with 1.14 milliseconds. That is super fast, right? So that's a 98% increase in CPU performance. It was using 2.34 megabits per operation. Now it's using 1.24. So that's a 48% increase. And then allocations, it was using 423,000, which we knew it was really bad on purpose, down to 9,000. So overall, the improvement is fantastic. I'm really happy with that. Remember, I told it to do a play-by-play? Here's all the commands it actually ran, which was pretty neat. I learned a few things by using the grep to look at the output of the actual profile, so that's kind of nice. I still look at the torch graphs quite a bit as well, because that's human readable, but of course this is AI, and it doesn't need to be human readable, so it just goes ahead and cranks through them. Then I had a summary of all of the fixes here, which is really nice. And so if I was doing profiling, or if I wanted AI to do profiling, I would want it to explain to me what was the fix, why did you do it, and what was the actual difference when it was done. So really, really great summary. All right, so that's how it did. But here's my issue. It did a couple of things that I didn't find, which is great, but it did a couple of things that I would never do in my code. So when I was all done, I had to go ahead and write up a summary of what I would have done and what it did and what it didn't do right. So again, here is the final performance metrics, and I had to compare it to what I had done in a previous run as a human and what it had done. And so it actually did about 2.5 times faster than I did as a human. Now remember, faster isn't always better if you have to sacrifice readability or other factors. Bytes per operation, I actually did better than it did. And that's because I recognized that I could use a ruin instead of a string in the map lookup. It actually took and removed the entire map lookup by using unsafe, and I actually kept the map lookup in there, so I was safe, and I was still actually had better performance. Now, it had quite a few less allocations than I did. And the speed up on the baseline of human to AI clearly crushes it, right? They got a 61% improvement in throughput. I got a 21% improvement in throughput. And what did AI find that I didn't find? Well, loading the entire file into memory, which I was doing, they eliminated with a bytes.buffer.read from. They went to the unsafe.String. Now, I don't like to use unsafe for a lot of reasons, but that doesn't mean that it really is unsafe. Unsafe is specifically there for when you know you can do this, but you're going to take on all the responsibility for it. And there's plenty of different projects I've worked on that use unsafe, but we, as a rule, try to avoid it. Now, that being said, if this truly was a pain point in your code, this truly was where you had to optimize, then unsafe would be okay. But now you're responsible for the life of that code because you're in unsafe. They created the ASCII fast path using the custom is letter and is space. So when it wasn't Unicode, they could go ahead and very quickly drop to ASCII, and that sped that up quite a bit. And then they did the byte offset tracking. Instead of building a slice of ruins, they created a zero allocation with the offset tracking to do that as well. And then they pre-allocated the map. Again, I don't like doing this, but in this case right here, I could probably live with it. And then they did the manual UTF-8 decoding. Only one they detected it was not ASCII bytes. All right. So what did the human find, me, that AI also found? So we both encountered the buffered IO issue, and we both eliminated string concatenation. So that is where we agreed to both of these. Now, what did the human find that the AI missed? The human's buffer reuse for read rune, okay? Allocated the buffer equals the byte, passed it once, and that was really a surgical fix that the AI never applied. Instead, AI blew past that, loading the entire file. Now, this is actually a meaningful optimization technique that's broadly applicable by streaming scenarios where you can't load everything into memory. So where AI did better is they were 2.5 times faster in clock time and had 64% fewer allocations. And it was profile driven, right? So it was methodical. It had 6 fixes, each guided by pprof data with benchstat comparisons at every step. The optimization summary documents 37 commands showing exactly what it did. But where did humans do better? Well, we did better because we didn't use the unsafe. It goes on and on about this, but really the one thing that you can typically count on is that if you see unsafe anywhere in your regular code, it's typically a code spell. It's fragile because it requires a lot of future refactorings because it doesn't make any guarantees from one release of Go to the next. So you are really taking all that on your own. And it goes against Go's philosophy of safety first. It's typically flagged by linters and security scanners. The other thing is, too, we already had a 21 times speed up without touching unsafe, which is pretty excellent. But decisively, here's where it comes in. It's readability. This is where I definitely win over them. If you look at my code, it's 41 lines. It's immediately understandable and very clear what's going on. If you look at the AI version, it's 83 lines requiring significant cognitive discipline to look at that and understand what it actually did. So my code can be read by most Go developers, even junior developers. So if they're coming in here to make any changes, it's very unlikely that they're going to have any actual bugs that they introduce. But the AI version requires a senior level Go person to even come in here and start tromping around on it, because there's a lot of stuff that you really have to understand before you even start to make that. Now, overall, I think AI did a good job. I think that if I was going to build a skill for this, then I would easily add a lot of the issues in that skill, saying try to avoid unsafe, try to make readability your priority, do all of these things. And only when those things don't work, and I've told you that this is still critical, then you could kind of go off the rails a little bit and use unsafe. You could sacrifice readability, those things. But until I tell you that, I think it's really clear if I was building a skill, I'd have to do that. Now, this is the first time I've ever used AI for optimization. It was just kind of a fun thing to do. But fundamentally, if we look at the verdict we're done here, humans still win. Now, with a little bit of skill manipulation, I think I could make this as good or better than I do this myself. But it's only better because of what I know. It wasn't better on its own. And that's the thing I keep talking to people all the time about AI, is that when you're getting bad results from AI, it's not AI's fault. It's your fault. You didn't train it. You didn't tell it. You didn't give it your experience and your knowledge. If you give AI your experience and knowledge, watch out. It's going to be fantastic. All right, well, that really wraps up what I wanted to show today. I hope you had a good time watching this. So here's what I want to know from you. Have you ever pointed an AI at a performance problem and been surprised by what it found? Or does it always find the obvious stuff? So drop that in the comments. I'm really curious to see how everybody else is using AI to do any type of performance profiling. All the code and benchmark results are linked in the description. If you want to see more AI-powered developer workflows, hit subscribe. I release 2 to 3 videos a week, real workflows, real tools, no fluff. I will see you in the next one.